Hey everyone, how are we doing? Happy Monday morning, week of the test. You know what I might do? I might set some stuff up here real quick. I have an idea. I have ideas. Where is it? What does that say? Cartoon strings. We can change that. If you're in the chat, feel free to say hi. We're just chilling out for a moment while Brian works on some Stream Deck stuff, getting some streaming stuff working. I've had ideas and then I forget them. That's how ideas go, right? Good morning, Angel. Great to see you here. I am going to make some quick changes on the Stream Deck. Stream Deck 1. Here we go. Let me go here and say music. Where's folder? If you have questions, drop them in the chat. We should put up the taking questions thing. Where's the taking questions? Taking questions. Taking questions. There it is. We're now taking questions. Good to see you here, Angel. How's your morning going? I need a folder. Should I just copy that folder? Where's the folder? Where's folder? No, we don't want to copy that. Folder. Oh, you can search. Good. Folder. Create a folder. Call it music. Okay. Copy the music there. Yes. Working. I have two of these open at the same time. It's going good. Got coffee, so that helps. Yeah, nice. Awesome. Glad to hear that. Coffee's a huge help. We are just copying music as we do this. It's sad. It takes so long to go back and forth. I have to click multiple times. I am putting the music directly on here so I can click. It is playing the music now. Good. To click around a whole bunch. It's a lot of clicks. If you have questions, let us know in the chat. Brian takes and copies all. I haven't played that one in a long time. I'm gonna have to learn where all the music's at. I've always thought the music should be easier to get to because I have to go within subfolders to get it. So I'm like, why don't I just put the music right over here so I can just be like, there we go. Change the music like that. Because I click the music a lot. So I'm like, why don't I set it up a little bit better and have a music? And I'm like, I don't have a billion. I click, what did that do? That's fine, I'm changing the button. If you have questions, let us know. Chapter 13/14, big chapters. Whoever go Canvas content, yeah, let's do that. Let's get that going. I've got enough music going over here. Yes. Okay, I'm good to go. Let me go back to the original Stream Deck profile. There we go. We're good to go. Let's get some Canvas content going here. Canvas content. Canvas content. What did that say? Reactive. Noise. Okay, online UTK. Let's check out some Canvas content due tonight. Assignments. Need a notepad. I thought this computer updated. It's saying it still needs updates. Okay. Canvas content due tonight. Tonight is the 7th, so it's sampling distributions. Okay, we got that up. Even else, we got to drop you some points, Angel. Thank you so much for being here, Angel. Mewbot's awake over there. Points, add, plus, viewers, 5,000 points, Angel, for being here. Asking the questions that I'm sure people are wondering about that Canvas content. I think I've got it ready to go. Let me make this a little bit smaller. I reset my computer. Is that Keith in the chat? Keith, good to see you here. Keith, hope your day is going well. There's so many point levels. There's even beyond points levels. I'm adding points right there. So let's see right here. We're at the 613 stat 201. Good to see you, Blake. Canvas content number 7. Let's go check it out. Setting stuff up over here so we can just change the music and turn it down. Victoria, good to see you here. It is time for some Canvas content. That's what people are wondering about. So here we go. Do not start the quiz until you're ready. You know what we say? I'm ready. I'm ready. I'm ready. Ooh, I can't sing. Okay. The three conditions for the sampling distribution must be met in order to calculate p hat. What are the three conditions? Who knows condition 1 for the sampling distribution of the sample proportion? What is condition 1 for the sampling distribution of the sample proportion? This is a review from last week. What is the condition 1 for the sampling distribution of the sample proportion? Here's a hint. What is condition 1? We have to randomly select things. We have to randomly select. MuBot loves some randomness right there. Condition 1 is random. What is condition 2 for the sampling distribution of the sample proportion? Condition 1 is randomly select the things. So if you're going to go talk to UT students, do sample less than 10%. That's the confusing one, is the less than 10% condition. So sample less than 10%. Condition 3 is the success failure condition for the sampling distribution of the sample proportion. And I've literally mentioned the conditions. This is under the formula sheet, which you can use tomorrow night for the test. These are the conditions for this right here, the sampling distribution of the sample proportion. The sample size has to be big enough so that both NP and NQ are at least 10. That's success failure, correct. So those are the three conditions for that one. The three conditions for the one we are going to do today are random, 10%, and large enough N, which is large enough sample size. More on that later today, but the third condition will depend on which one you're doing. Wednesday night, you got it right there. So with this right here, let's look at the question again. It mentions the conditions, and then it says to calculate p hat. For 1,000 points, what is the formula for p hat? P hat stands for sample proportion. What is the formula for p hat? We reviewed this last night during the Kahoot. So what is the formula for p hat for 1,000 points? What is the formula for p hat? What is the formula for p hat? What is the formula for p hat? I'm not going to be able to change that easily. The formula for p hat is x over n. X over n. So that is just a mathematical formula. Do we need to meet any conditions? If I tell you something like, I talked to 5 people and 2 of them like cookies, do you need to calculate the proportion of people who like cookies? Do you need to do any sort of checking of conditions? P hat stands for sample proportion. What is the sample proportion of people who like cookies? I talked to 5 people and 2 of them said, yeah, they're awesome. So what's the sample proportion? It's a 50-50 guess. So before we guess at it, we should be like, what's the sample proportion? So remember, p hat is just sample proportion. That's all it is. There's no conditions for it. It's just sample proportion. The sample proportion, if you talk to 5 people and 2 of them say cookies are awesome, the sample proportion would be 2 out of 5, where 2 is the amount of successes, X, and then 5 is the amount of sample, the size of our sample. So why do we check the conditions? Why do we check the conditions? Here's a hint for why we check the conditions. We check the conditions such that what? Why do we check conditions for the sampling distribution? Great job, Angel, right there. Good practice. Why do we check conditions? The reason we check conditions is because if the conditions are met, then what? Meeting the conditions means what? If we meet the conditions, then the sampling distribution of the sample proportion will be, or approximately, it'll be approximately what? Meeting the conditions means that the sampling distribution of the sample proportion is going to be what? And then we can model it with this. Woo! It'll be normal. Does that make sense? So if we meet the conditions, so what's the answer to the first question? We reviewed a lot right here. So that's a lot of review right there. What's the answer? To calculate p hat, you have to meet 3 conditions. True or false? To calculate p hat, you have to meet 3 conditions. True or false? How do you calculate p hat again? How do you calculate p hat? So let me check your knowledge right here. You ready? We talked to 10 people and 3 of them say bunnies are the best animal. What is p hat? So we talked to 10 people, 3 of them like bunnies. What is p hat? bunnies in the chat. What is p hat? P hat is sample proportion, the proportion of the sample that responded in the affirmative question. Point 3, right? Did you check any conditions right there? To calculate the sample proportion, did you check any conditions? To calculate the sample proportion, no, you didn't. So the answer is false. And why do you check the conditions? Why do you, like, if the conditions are met, we should say, then what does that mean? Meeting the conditions of random, less than 10% of the population is sampled, and there's at least 10 successes, at least 10 failures, means what? To see if the sampling distribution of the sample proportion is approximately normal. Good job, Wes, right there. Good to see you here. So, and good job, Angel, right there. To see if it's normal. So we are checking the conditions to see if we can model it with the normal. If it meets the conditions, we can model it with the normal. Can you calculate sample proportion at any time? Yes, because sample proportion is just amount of successes over amount of total trials. Like, what proportion of my cookies are chocolate? I don't know. I just want cookies, apparently. So this right here, we can calculate sample proportion at any time. All other things being equal, the larger the sample size, the smaller the standard deviation of the sampling distribution. So there's actually 2 standard deviations. What is the standard deviation formula on the screen right now? And you can, if you know the notation, you can see it. What is the, and I've got it also color-coded to help out, what is the standard deviation formula? And there is another one. Well, the other distribution we're going to talk about later today is normally distributed with a mean of mu and a standard deviation of sigma over square root of n. I'm giving away a hint right there. So that's the other sampling distribution. So what do you notice about these? Good to see you here, Evan. What do you notice? It said all else being equal, larger sample size leads to smaller standard deviations. What do you notice about these? What do you notice about these? It says all else being equal. Oh, it's practice. We got to know what the formulas mean. That's just the standard deviation right there. So it says all else being equal. Oh, no worries, Evan. We're practicing. We're going to do a few versions of this. We're going to make sure we understand that this means the mean of the sampling distribution. And we could just, and that's how you calculate the standard deviation. So that's both things we covered. Yes, last class and today's class are on the screen right now. So what do you notice about the standard deviation? N is where? What do you notice about the formula for the standard deviation? Because all this is the formula or the way to write out normally distributed with a mean and a standard deviation. So second value, N, well, it's not, well, kind of, it's in the where. The N means normally distributed, with a mean, whatever that value is, and a standard deviation, whatever that value is. And N is where? Well, the capital N means normal. The N I'm pointing to right here is where. This N right here, which is lowercase n, sorry, that one looks weird. That lowercase n is where. These lowercase n's are where. Yeah, I meant lowercase. Good call, Evan. The uppercase n means normally distributed. It's under the square root, but it's also where. Both n's are where. Below the p times q, and so we're dividing by n in the denominator. So let's look at the question again. You ready? All other things being equal, the larger the sample size, the smaller the standard deviation. So what do you think? If sample size is larger, what happens to standard deviation we calculate? If sample size is larger, then the standard deviation will get what? Because it'll get smaller. So that's mathematically true. And all else being equal, because there are weird scenarios where like you change what P and Q are, or you change sigma, but everything else kind of being the same. If n gets larger, your standard deviations get smaller. And think about this. That means there's less uncertainty because standard deviation is variation in what you're sampling. So just theoretically, if you understand standard deviation is variation, so there's less variation if you sample more on the understanding of what the average would be. That's a little bit more complex, but the math right here hopefully shows it that since we're dividing by n, it is mathematically true right there. These are tough ones. A lot of people miss these. And what do you think? I think Evan knows. We got a new Leo in the chat. I think it's Evan or Blake. What do we need to know to solve this question right here? What do we need to know to solve this question right here? This question up top, we have to know what? What do we have to know? Notation, brother.
Notation, brother.
Okay, let's write this down right here. You ready? A manufacturing company would like to investigate the effect of a new supplier's raw material to their product. The company makes 7,000 of these items each day. So they're going to investigate their daily source of products. They're investigating their daily products. So to investigate their daily products, what would 7,000 be? This one's a weird notation, but they're going to take, this is their daily product that they want to understand. So tell me in words maybe, and I'll tell you the notation for it. So tell me in words what that is. Tell me in words what that is. That's their daily product. Not quite predicted. That right there is how much product they make a day. That is their full population. And so that is technically the notation capital N, not for normally distributed though. That's their population size. They're taking a sample of 500. Now that's easier. So the sample of 500 they take from this daily is what? Because they're seeing if their daily product is good. So this sample of 500, easier on the notation, is the what? Like that one we've practiced a lot. That's their sample size. So what is the notation on that? What is the notation on that? This one we just did a second ago. What is the notation on their sample size of 500? And use the formula sheet if you want. Where's that formula sheet? To remember that you need to know we're doing proportion of defect. So sample size is what? Sample size is what? I've highlighted somewhere up the answer. No, it's on the screen right now. Take a screenshot if you want. So sample size is what? Sample size is what? What is sample size is what in notation? If you're watching this, make sure you write this down. Make sure you practice. Write it down. P is true proportion. So P is true proportion. N is sample size. N is the amount of sample we take. So N is sample size, like number of sample maybe. And then capital N, which we don't really use much, is population size. Also stands for normally distributed, but that's just statistics doubling up on things being used. So sorry for any confusion. We don't really use capital N in formulas. It's just an idea that exists, like the size of the population. So right here, we have that N. Can you check right now? If you know the size of the population is 7,000 and you know we took 500 from it, what could you check? And I'll show you the math right here. I think that's about right. Yep. And so right now we're going to check, and we're going to check that next one. You got it, Wes, right there. Does everyone see what I did right here? We took a sample. Wes is correct right there. No worries, Blake, right there. Exactly. And then this right here, what does that equal to? That is seeing if our sample, so does that make sense? We sampled 500 and our sample size of 500 is less than 10%. Let me check my math. I did it in my head. So it's about that. Yeah, it is 7.1. It's less than 10%. We sampled less than 10% of the population. There's the rat. So you see it right now, right, Evan? So our sample size of 500 is 7.14% of the total population of that daily output of 7,000, which is less than 10%. So we sampled less than 10% of the population. Does that make sense? That is how you check the 10% condition. A lot of people forget how to check it. You check it by seeing, is my sample size less than 10%? Yeah. So this is sampling distributions right here. You see, what is my sample size? And great job, Evan, right there saying this is N over capital N, not normally distributed N. But that is sample size N over population size N. So is my sample size less than 10%? Well, then see what percent you sampled. That's the percent we sampled of the population, and it is less than 10%. So the next question, which is the real question, is saying if the success failure rate is greater than 3%, which we're talking about the defect rate. Now, you wouldn't have a crazy defect rate. Student one time said, what if it's like 100% defect? Well, I gave him points back because I was like, well, I guess theoretically you're right. But you probably have smaller defect rates. The company's going to get shut down. So this is saying if it is, and we should have just said equal to 3% here. Wish we change that. If it is equal to 3%, then we're telling you if the defect rate is 3%, I've just told you what? If the defect rate is 3%, I've just told you what? The defect rate, something is a defect or is not a defect. If the defect rate is 3%, I've just told you what? So I'm saying if the defect rate is 3%, that's the proportion of defects. I've just told you what? What is 3% in notation? Because this all boils down to knowing the notation, knowing how to read the question. If you don't know the notation, the questions don't make sense. So if the defect, well, so we'll see. So, but what is 3% in notation? What is that in notation? No, don't worry. What is 3% in notation? What is 3% in notation? It's the defect rate. So what is the defect rate? Hint, it's the proportion of defects. And so go to your formula sheet. We're doing proportions. So you have to be like, what is the defect rate in notation? The proportion of defects. What is that in notation? What letter do we use for that? A lot of these questions, especially the later chapters, boil down to knowing the notation. You know the notation, just like, so it's 0.03. And so what is 0.03, like the letter for it? Not the standard deviation yet. It could technically be Q. Either one is fine. Probably P if we're looking at like we want to understand defects. It's weird to say that defects are successes, but if that's what we want to understand, then it's probably P. But if it's Q, it's fine because P and Q are just complements of each other. So that is P right there. So it asks us to check the success failure condition. How do we check the success failure condition? What mathematics do we do to check the success failure condition? So write this down. If you see success failure condition, good day, Victoria. Good to see you here. What mathematics do we do to check the success failure condition? So what math do we use to check the success failure? No worries, Evan. What math do we do to check success failure? Q is a failure, technically, in notation. P is success, Q is failure. P is proportion of successes. X is amount of successes, P is proportion of successes. The thing we're interested in, but you can switch what you're interested in for P and Q to switch. So what is the mathematics right here? 0.97. Because P and Q are complements. So P is 0.03 and Q is the complement, 0.97. So you just do 1 minus all the way up to the chapter that ends today, chapter 7 through chapter 13. Check out review 2. Review 2 has all the material on it for the exam. Check out review 2. Review 2's got the material. So what is the mathematics? Can we throw either or both of the homeworks in the quiz tomorrow? Yeah, we could do that here next. We could probably do the homework. Might not have enough time to do the quiz. Probably try to get through the homework pretty quickly. So what is the mathematics to solve this right here? So when we check the success failure condition, what is the math to solve it? N something times has to be greater than or equal to 10. Well, you can call it the defect rate. You would just be switching them. It's just what you're interested in. It's like you can switch it. It's just like if you want to call because you might be interested in monitoring defects. So someone might say a defect is a success. Success doesn't mean good or bad. It just means the thing you're monitoring. So you might be wanting to monitor your good product maybe. So that's why we label it like a success. So it's just, I'm sorry, Victoria. No, it's a busy week. A lot of teachers divide the semesters into thirds, and then because of that, a lot of tests land on the same time. So you see a lot of midterms around the same time for people divide it in half, and then so that's why a lot of tests are usually bunched up around that third mark. I don't know. It makes me wonder, like, should we just do mini tests at all times? Like, have a weekly. I don't know. That's why we do Canvas content. So that way you have more grades, and it's not just like everything's the test. I'm sorry, it's tough. That is tough. What is the mathematics to check success failure? Mind bring up the notes right here. Good luck on your exam tomorrow, Victoria. No mini tests. Well, don't worry, we're not changing anything now. What is the mathematics to check success failure? I'm bringing up PowerPoint right now. What is the mathematics to check success failure? I'm going to bring up the notes. So help me out right here. You got this, Victoria. Stay strong. You got this. I'll tell you the biggest thing in life is staying positive, meeting people, and helping people. Because if it's not all about grades, because I'll tell you this much, I didn't make the best grades throughout my life. Hey, Lachey, good to see you here. 1 minus P is the formula for Q. 1 minus P is, and good job right there. 1 minus P is the formula for Q. So the success failure, I mean, try to do well on your test. That's important. Doing well on tests is important, but it's more important in life how we treat each other and help each other throughout life. So what is the way we check mathematically success failure? So I've got the notes up. So the way we check, here, let's go here and do Control F and type success. And there we see successes right there. And here we go right here. Here's the success failure. So how do we mathematically check success failures? And this is why knowing notation is so important. How do we mathematically check success failures? What do we do mathematically to check the success failure condition? So have this written down. Like this is, you want to write down, to check the success failure condition, I need to see that what? Evan, you're on the right track right there. And that's what you're doing right there. You're doing NP needs to be greater than or equal to 10 and NQ needs to be greater than or equal to 10. So you're going to check both of them. So as The Rock would say, it doesn't matter. Because we're going to be checking both. And so we're going to see both are greater than or equal to 10. So Evan, that's a good job right there. So the mathematics is NP needs to be checked, NP and NQ. So what is important to know? I can't stress this enough. You need to know how to find your what to start these questions. What do you need to know how to start and find? So I'm going to solve it over here. What do you need to solve and find every time? So you need to find your notation, right? You need to find your P's and your Q's. Do we pass the success failure condition? Do we pass the success failure condition? The answer is right here for if we pass or not. Do we pass it? And then you have to try to explain why. Do we pass the success failure condition? Yes. And why? Great job, Wes, right there. Yes and why. That is correct. And then say to me why. Because what? We pass the success failure condition because, not 0.10, not 0.10 though. Both, there are at least 10 successes, at least 10 failures. And great job. Thank you, Evan, right there for the practice. And that's why I ask everyone to say it, because if I say it, it's one thing. I want you to say it, and then to say there are at least 10 successes, at least 10 failures. Now, what's confusing is, remember, we just did 10% to check to see if we sample less than 10%. So that's why I stress that we practice this, because the 10% condition is that we sample less than 10%, which is where we see if the amount we sample over the total sample size is less than 10%. That's the math there. For that one, you have to find the population size and you have to find the sample size. And for this one, you have to find NP is less than or equal to 10%, or excuse me, 10. See, I just made the same mistake. I just did it. And then NQ, which is the amount of failures that are expected, is less than or equal to. Oh my gosh. Please. Wow. Oh my gosh. Wow. Be very careful. I literally almost made big mistakes right there. At least 10 successes, at least 10 failures, less than 10%. You didn't see it? Well, I saw it. It was, it's very easy when talking about both conditions to make these errors. So you want there to be at least 10 successes, at least 10 failures. And if you meet these conditions, one last time here, if you meet these conditions, what happens? 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 Which is not happening here. If you meet these conditions, the distribution is normal. How many expected successes do you have in this distribution? How many, with a sample size of 50 and a proportion of 0.01, how many successes do you have? How many expected successes? And the answer's down there on the bottom if you want to see it. So how many expected successes do you have? Not 5, close, not 5. not 5. 5 would be that. That'd be for 5. 0.5. So notice, as I increase this right here, what does the distribution start to become as you have more expected successes? As you have more expected successes, the distribution becomes more and more normal. And we say it's approximately normal at a certain point, and look at the expected successes, which is 10. It's not perfectly normal, but it's approximately normal, we say. It has no skew when it's at the 50-50 mark. That's where it would actually be perfectly normal. But we say approximately normal or good enough to use the normal distribution. So you have to meet the 3 conditions, whichever one we're doing, the proportion distribution or the mean distribution, for the distribution to be approximately normal. Condition 1, condition 2, condition 3. More on that today as we review. Okay, so was it met? Yes, it was met. We had 15. Which of the central limit theorem relates to which of the following conditions? It is going to be the nearly normal condition, also known as the large enough n condition. This is going to be covered today. Condition 1 says we randomly select. Condition 2 says we need less than 10% of the population. And this is the third condition for the distribution of the sample mean. So notice, both of these have the same 2 what conditions? How many conditions do they have? 3. And they have the same 2 what conditions? So both of these have 3 conditions. And how many of them are the same? And I'll show you right here as you're thinking that over. Here's condition 1, condition 2, which we did last class for the sampling distribution of the sample proportion. Here's condition 3. Here's today's material down here. Here's condition 1, condition 2. And then here's condition 3, also known as the nearly normal, which basically talks about success failure also. But remember last class we talked about first 2 are the same exactly. It's still, and look, this is the sampling distribution of the sample mean, which we are covering today. Highlight that right there, sample means. And then over here, this is the sampling distribution of the sample proportion. Just look at that tiny change, how it changes just barely, where you see proportions right there and then you see means. It's literally the same slide except for the change right there. So it's literally the same slide. Just to show you again, watch it change. It's literally just that right there. So it's checked the same way until you get to the third condition, which deals with it being quantitative data. And we'll talk about what the large enough n/nearly normal condition is when we get to it today. But that deals with the central limit theorem, which states that it will become more normal as the sample size increases. More on that today. So that is right there. When the population, mean, and standard deviation are known, which distribution is used? So what is the only distribution you know? If you've been following along, what is the only answer you would say right here? 1, 2, 3, or 4, which is the only one we've covered? This is a really nice question if you've been following along the class, the normal, right? And that's why we check the conditions to see if it's normal. We haven't talked about the t, we haven't talked about the chi-square, we haven't talked about the f yet. So if you follow along, you'd be like, oh, well, the only one we've talked about is the normal, so got to be the normal, right? Yes, you are correct, because that's why we check the conditions. 10 out of 10. Let's do one more preview of this, and good work, everybody. Good practice. Be writing down the notes. The 3 conditions must be met to calculate p hat. Great job, Blake, with that 10 out of 10. True or false right here? Let's see. True or false? The 3 conditions must be met to calculate p hat. True or false? False. Because p hat is what formula? What is the formula for p hat? You can just solve it. I can tell you, I talked to 20 people and 15 liked bunnies. So what's p hat? Like, know how to calculate p hat like this. Be like, oh, it's this. X over n, great job, Angel, right there. So it'd be 15 over 20, 75% of people like bunnies. That's false right there. The success failure condition states that your measure must be binary, either a success or failure. I'm a little worried on this one. Okay. I'm gonna get really mad. What does yeah. So it doesn't state that. It would require it. So this I'm saying false right there. The success failure condition states that you must what? What does it more like if you had to describe to someone the success failure condition, what would you describe it as? You must have what? How would you describe it? I wouldn't describe it that way. I would say it requires success failure data, but success failure condition says you must have at least 10 successes, at least 10 failures. So that's really not what it's saying. It's not about it being binary. That's kind of required, but not what it says. All else things being equal, as the sample size increases, the standard deviation gets smaller. Why is that true? There's sample size right there, because the sample size is where in the equation for both of them. The sample size is where. We're doing it a little bit quicker this time. Then we're going to do the homework. The central one relates to which of the following conditions? Which of those? Which of those, Evan? You're correct, Evan. That's correct. It's in the bottom right, Roshni. So since it's in the bottom, if sample size gets larger, then that will make a smaller standard deviation for either of these as sample size gets larger. So that is very, very true right there. The 10% condition states we need to sample no more than 10% or we need to sample more than 10%. Less than or more than. What does the 10% condition say? Which is a bit of a weird one. So the 10% condition says no more than or we need to sample more than. So less than or more than. Which one is better? Which one should we be doing? No more than, which is less than. It's a bit odd, and we show the mathematics here on how to solve it, that the sample size of n is less than, or excuse me, when you divide by capital N, population size, it's less than 10%. That is how we solve that right there. The central limit theorem relates to which of the following conditions? It relates to the nearly normal condition, which is basically the way we have the success failure right here, and we're showing it on the screen over here. If you do not have at least 10 successes, at least 10 failures, your distribution will not look what? If you do not have at least 10 successes, at least 10 failures, so you see how there's only half a success down here? Your distribution will not look what? It will not look what? If you do not have at least 10 successes, at least 10 failures, it will not look normal. Great job, Lachey. More points in the chat. So it will not look normal. And that's got it. Another 10 out of 10. Hopefully. That's why we check the conditions. There we go. When did I do it? 28 minutes ago. Attempt. Oh, that's the recent. Okay. Should we do the quiz here? Or the homework? Let's do some homework. Well, we got the music queued up. Can we do the quiz? Which question on the quiz? The waiter-waitress question? Which quiz question? You name it, we do it. I'm logging in right now. Quiz over homework? I moved the music over to the right. It's a big help. Quiz. We could probably do the full homework if we wanted. Which quiz question? Almost got the homework up. We should maybe try and knock out the full homework. Let's try and knock out the full homework real quick. So we can get that done this morning probably. Let me see. Okay. Pearson had trouble loading. No, Pearson, no. Stats 201. Chapter 14. Homework. I was more concerned with me giving up my feedback on their website. Nice. Yeah, I think we're gonna do homework. Let's check it out. You ready? Here we are with the homework, because I think Victoria, you said homework, right? So let's do that. Okay. A food company sells salmon to various customers. The mean weight of the salmon is this. Okay. So we have to know our what to solve any of these questions. We have to know our what to solve any of these questions. What do we have to know to solve questions here? What do we need to know to solve these questions?
Notation, brother.
You have to know that notation, brother. So it says the mean is this and the standard deviation is this. What are those? It says the mean is this, the standard deviation is this. Stealing Blake's shot right there. Nice. It says the mean is this, the standard deviation is this. It's saying they are these. They know them. So what are those values? So what are those values? It says the mean is this, the standard deviation is this. That is population size and that is sample size. So it wouldn't be those. No worries, no worries. Have all these written down. So it says the mean is this. Mu is the mean. So it's telling us, it told us mu. So that is mu is the mean. And close SD is a way to abbreviate standard deviation. Also, sigma is the true standard deviation. So mu is true mean. So when it says the mean is this, that makes this mu. And when it says this is the standard deviation, that makes this sigma. And so now it says the company ships them to restaurants in boxes of 9 salmon, to the grocery store in 16. Oh my gosh. So they're doing two things right here. They're being tricky. N1 is 9. What do you think I'm trying to differentiate between? The subscript right there just means sample size what? Oh, and then discount outlets. Oh my gosh. Oh, I know what they're going to show you here. I know what they're going to show mathematically. It's not. It's kind of like a cluster. It is good answers right there. I like that. But those are sample sizes 1, 2, and 3. Does that make sense? Sample size 1, sample size 2, sample size 3. So those are just different samples that these stores are getting. Does that make sense? These are different samples that the stores are getting. I know what they're going to be showing you. Find the standard deviation and the mean weight of the salmon in each type of shipment. Find the standard deviation of the mean weight of salmon in boxes sold to restaurants. So restaurants are getting it in boxes of 9. So it's going to be sigma over square root of n. So we go right here and we say 35 over square root of 9 is equal to 35 over 3, which is equal to 11.66 repeating. Does that make sense right there how I solved it? I just had to know my sigma, which is 2, and I got it wrong. See, you got to check your work. Brian's brain is booting up. I chose the wrong numbers. Wow. Gotta watch what I do. There we go. 2 over square root of 9. Great job, Evan, right there, watching and getting it right. 5,000 points. Yep, you thought right. Brian grabbed the wrong numbers. That's why it's all about
notation, brother.
You have to grab the right notation, and we have sigma over square root of n. So that is going to be the standard deviation, 0.66 for the first one right there. So make sure to write down the right numbers. Don't make errors like Brian. 2 decimal places, so that's going to round up because it's 0.66 repeating. Should be right. Oh my gosh, what am I doing today? Sigma over square root of n. Square root of 9 is 3. Standard deviation of 2. Restaurants. The boxes sold to restaurants. The boxes sold to restaurants in boxes of 9 salmon. The standard deviation to 2 decimal places. What would you do if you answered this way? What would you do if this was your answer? Well, first off, what's the right answer? And what would you do if this was your answer? Because read what it says. Victoria, you got another 5,000 points. That is correct. And you could also email Brian. Yes. I was like, what did we do wrong? I mean, I know I made that one typo, but we just didn't round. So great job, Victoria. Good catch right there. It's 0.67 it is. So it's sigma over square root of n. So here's what they're showing you. This question is meant to illustrate the point that as the sample size gets larger, what is going to happen in here? As the sample size gets larger, what happens to the standard deviation of the sampling distribution of the sample mean? This is the sampling distribution of the sample mean. What is going to happen as the sample size gets larger? So now it's going to be 2 over square root, because they're doing the next one, right? Grocery stores get 16. So, and they're using perfect squares right here. So 16 square root is 4. So 2 over 4, it's 0.5. They're showing you, and they're really nice because they're using a perfect square there also. So it's going to be 2 over, so that's going to be 0.22, right? 2 decimals, check answer right there. Good. They're showing you that it's getting smaller. So wait, did you? Yes, I think so. Let me make sure I did it in that order. Yes, I did use N1, the first sample size. So it's the first one, the second one, the third one. And they're showing you that the standard deviation of the sample mean gets smaller as N increases. and they're probably going to illustrate that here. So just doing it by changing what the sample size is, changing this from N1 to N2 to N3 in that order, you will get the answers. And you notice as you increase the sample size, this starts to get smaller right here, changing the sample size. So if mine is sigma 4, no, and N1 equals 4, I would expect 2 is the answer. That does sound correct. Yep, because you would be doing sigma is 4, your standard deviation is 4, your first sample size is equal to 4. So then you get 4 over square root of 4, which is 4 over 2 equal to 2. Yep. And then, yeah, good work right there, Blake. Good practice. That does sound correct. Just make sure to know your notation, know how to solve it. It's just showing you sample size increasing and standard deviation getting smaller. The distribution of the sample, the distribution of salmon weights turns out to be skewed to the high end. Oh, would the distribution of shipping weights be better characterized by a normal model for the box or pallets? Explain. Choose the correct answer. So I think it's only the pallet right here. Okay, so they're saying a carton, and they're talking about the box right here. They're talking about the box of 9 versus the pallets. So this is the final condition. Do we have enough time to attempt one problem? Yeah, we'll do that here next. Researchers, yeah, we'll do waist sizes. We can do that one, Victoria. We got time. So this is talking about the third condition right here, which is going to be the large enough n condition, nearly normal large enough n condition. And so when we do this third condition, depending on how skewed the distribution is, if it's very skewed, we need at least 100. But if it's only a little bit skewed, we need 25. So, or just kind of skewed. This is 25 is good enough unless it's heavily skewed. So notice what they tell you right here. They say it's skewed. So you need a sample size of at least what right here? We need a sample size of at least what because it's skewed. Not heavily skewed. Since it's skewed, not heavily skewed, we need a sample size of at least what? If it's heavily skewed, 100. If it's kind of skewed, 25. 25 is usually good for most, but if it's heavily skewed, 100. 100 is the extreme. Like if there's big problems, 100. If there's some problems, 25. More on this today. So this is the third condition. It says to the high end, though. High just means right skew. So this is right skewed, but if it's a heavily or strong skewed or very large skew, so with this, the boxes, so the pallets, which of these would be more normal, characterized by the normal, the pallets, as long as, no, the pallets, because regardless of the underlying, that doesn't sound right. The pallets, because as long as the underlying distribution is normal, no. The pallets, because regardless of the underlying distribution, the sample size distribution of the mean approaches the normal as the sample size increases. Yes. Whoa. That is right there. So as the sample size increases, the distribution of the mean will become more normal. So as the sample size increases, the distribution of the sample mean will become more normal. And I'll be showing that with the central limit theorem applet today. So if you're wondering about that question more in depth, check out today's lecture where we'll show as the sample size increases, the sampling distribution of the sample mean becomes more normal. Really good practice. Condition 3, large enough n condition. Let's do that other question. This was homework question 1. Know your 3 conditions. No. Where's it at? Oh, I don't have my buttons
Know
labeled. Wait.
your variable types.
Get copyright claimed on that. We were loading up the quiz question. Thank you, Victoria, for the quiz question. Beautiful. That's Jason right there. Where's it? I thought I went to... Wait, do they not have... What have I done? 2 seconds. Said that we start on homework because I can't open the quiz. No! I'm looking for replace questions. Maybe they updated something. There it is. It wasn't there. I swear it wasn't. That was weird. Okay, waist size question, right? Waist size. There's Here's the waiter waitress question. Famous one. What's the quiz? There's one waist size question. Wait. Which one does yours have, Victoria? Is it, you ready? Is it question 1 or question 2? Which version do you have? Question 1 or question 2? Which version do you have? Here's version 2 or version 1? Both? We'll try to do both. All right. Good to see you here, Ava. So you're looking at the annual compensation of CEOs. We might have time. One more question, is it? We might just barely have enough time, Ava. We'll try to do that. We'll do waist size version 1. A waitress. Ah, the waiter waitress question. The classic one. Classic. Waiter slash waitress. The classic question. Waist size. Okay. Version 1. Waist. We do have office hours later today after class, so check out after class today. If we don't get to some of these, we'll do like a 15-minute buffer to start class. So we've only got 10 more minutes. Yeah. Okay, you ready? Let's work on these. Taking the timestamp as we talk. Chapter 14 quiz. Okay, let's do this. I was merely talking about version 2. I wasn't talking about. Oh, you were. Which one you was? Or you were version 2? Okay, let's go right here. Here we go on the waist size question. And so is somebody's waist size quantitative or categorical? Is the size of someone's waist quantitative or categorical? Is the size, you're welcome, Victoria. Is the size of someone's waist quantitative or categorical? How big someone's waist is? Is that a quantity or a category? Is that a quantity or a category? The size of someone's waist. The size of someone's waist, is that a quantity or a category? It's quantitative. How large is your waist? It's quantitative. So the reason it's quantitative is because we would measure it in inches, right? Or centimeters. I think they're centimeters. No, they're doing inches. So this is the measurement in inches. Now, the reason you want to know this is because you're going to now go and look at your where. You're going to now go and look at your where. Where are you going to go and look? You're going to go right now and look where. Once you know that this is quantitative, you're going to go and look where? The formula sheet. So let's go and grab the formula sheet right here on the sampling distributions. Let's grab this right here. And then let's bring it over here. Oh, open it on the other screen. There we go. Here. Drop it in. And let's go grab that question. You're right, the formula sheet. So now we take the question itself and bring it over here too. So now that we have the formula sheet on the screen, and good to see you here, Mary, we need to do what? We need to what? Our notation. So we can solve this now that we have everything on the screen, and we need to what? Researchers measured the waist size of 245 men in their body fat. The true, we got a little here, true mean, the true mean and the true standard deviation, respectively, for the men was this. So the true mean is this, and the true standard deviation is this. What are those in notation? What are those quantities? So what are those quantities right there? What are those quantities? Mu and sigma. Great job. Those are mu and sigma. So we just found here mu, and we just found here sigma. And do you know how many of these problems right here we just solved? These problems down here, we just solved half the problems. Because the mean, this value right here is the mean. That is the mean. So every one of these values right here is just equal to mu. Does that make sense? Because mu, it's asking for mu y bar, which is the mean of the sample mean, the expected mean of the sample mean, we should say. That is equal to mu. All those answers right there will be equal to what? Because you know that this is mu right here. So all those answers are equal to what? Because literally the formula for that first one is mu y bar equals mu. Mu equals 36.396. And that's the answer to all of them. Does that make sense? Every one of those will be 36.396. How does that work? So the understanding behind this is the following. If the average guy at UT is 5'9", we won't multiply. No multiply. Don't multiply. Don't multiply anything. It stands for the expected mean of the sampling distribution for the sample mean is equal to the mean. If the average guy at UT is 5'9", and you talk to 10 guys, what mean height would you expect to see? If the average guy at UT is 5'9", and you talk to 10 guys, what mean would you expect to see for the heights? So you talk to 10 guys, and the average height at UT is 5'9", then what is the mean height you would expect? 5'9". So it's that if the average grade on the Stat 201 second test is an 80, and you talk to 10 random students, what would you expect the average of those students' grades to be? So we're saying if I tell you the average grade on the second test was an 80, then what would you expect to see in a sample there? You'd expect to see 80. Notice how sample size doesn't matter.
It doesn't matter.
It's just saying the expected sample mean, because mu now stands for expected. It's weird that mu is kind of being used as expected, but the mean for the distribution of the sample mean, which would say the expected or average sample mean we should see, is 80. So if it is true the average of the 201 exam was an 80, you'd expect to see an 80. Does that make sense? Like if you sample, this is what you should see or expected to see in your sample. So all the answers to those questions on the left are simply the mean. But what does change? What does change about this distribution? What does change about this distribution? What does change? The mean stays the same. Like sample size is not part of the formula for the mean. What does change about the distribution? So the mean stays the same. What does change? And this is a very common error. People say, well, the standard deviation is this. Well, that's for just the full population. The standard deviation is 4.156. What changes is going to be the standard deviation for the sample mean. That changes. And that changes depending on the what. The standard deviation is going to change depending on the what. Because we're now solving for that quantity right here. The standard deviation, y bar is sample mean. Y bar is sample mean. So that says the standard deviation of the sample mean. So that'll change depending on the what. That'll change depending on the what. That'll change depending on the sample size. And if the sample size gets larger, this will get smaller. So we go right here and we do sigma over square root of n. And then we're just going to change what n is as we do this right here, so that we have the original sigma of 4.156 over square root of 2. And we're just going to plug in these different values over here. Does that make sense right there? It'll be sigma over square root of n. And this is like the previous question we saw, whereas n gets larger, the new standard deviation is going to get smaller because we're solving for the new standard deviation. So that is the quantity we want to solve for. Oh my gosh, Photoshop. Come on, Photoshop. What are you doing? You misclicked one button. Go away. Okay. So here we go. 2 square root 4.156 divided by... There we go. 2 point. Thank you, Blake. I appreciate that. I'll throw you some points here in a second. To 3 decimals. Be very careful. And then we're just going to take and do 5. So square root of 5. We're just doing the original standard deviation, 4.156 divided by square root of 5, which I square rooted in the background. And you should see it get smaller each time. If it doesn't get smaller, you've done something wrong. So if it does not get smaller, 3 decimals. If it doesn't get smaller, thank you so much. And then we go here and we go 10 square root. And then we go original standard deviation divided by that. Thank you, Blake, for checking the work as we do this. What'd you say? Probably not even Blake. Yeah, good practice. And then next we go 20 square root. And then we go, and so it's going to be a little bit less than 1. 4.156 divided by this. 9 point. And notice The mean stays the same. The theoretical mean stays the same, but the standard deviation gets smaller. How close do these theoretical values match the actual values? Now, here's what's neat. So be very careful. Your answers are going to be close to the table they show you. They're not going to be exactly. So here's the table of values, and they're showing you it's becoming more normal. So notice your answers right here, 36.396, basically the same. 2.9, there we go. 1.85, 1.3, basically, and 0.9. So these are kind of a guideline. These are what they saw. This is what they should theoretically be. Don't worry that they're not exactly. It's just that the central limit theorem states we should be getting close to these values. So those are going to be a good check right there as you do the work. And do check the mathematics I did to solve this. You're just changing what n is. The only thing that changes is that you're changing what the sample size is. As it gets larger, the standard deviation gets smaller. Just change what you plug in for n right here, and you will solve for each one of those values over there. So that's how I solved for every one of those. The theoretical values, they're not exactly. They're reasonably close to. The theoretical standard deviations are reasonably close to. They're both reasonably close. They changed this one a little bit. Use a sample size of blank since this is the blank sample size for which the sampling distribution is approximately normal. Is unimodal symmetric? Good. Let's look. Oh, it's not that. So the original population is not that skewed. Oh, is it going to be 5 or 10? Oh, man. Oh, I love that little smiley face breaking out of the ground. That's so cool. When did that happen? That's a cool one. Oh, my gosh. Okay. It's not that. Use a sample size since this is the... It's going to be smallest. This one I'm worried. If you, whatever you put for that, it's not skewed. They could even go 2-ish because it's basically normal to begin with. So since it's, do it right now. Wait. Oh my God. Chat, you're crazy. What about the shape of the distribution of the sample waste explains your choice in C? It's because it's basically normal to begin with. The distribution of waste size is unimodal and nearly symmetric. So the sample size of the distribution of the mean is close to normal, even for small sample sizes. That is correct. It's highly skewed. No, it's not highly skewed. Notice how I was noticing right here, it's basically normal to begin with. They might be going as low as 2. I feel that's the way they're going on this one. No, they went 5. Shouldn't second guess myself. Yeah. Once again, those are 5 minutes. You missed like the whole 5 minutes. See, I did. If you missed that question, just let me know. A lot of times if you watch these office hour videos, I'm like, that one's one that that's just where the subjectivity of it, because if it's normal to begin with, sample size of 2 is actually fine. That's mathematically correct. If it is normal. So I should have gone with my gut with 5, apparently. I was like, that's the only one I'm like, yeah. Just someone writing it. They change these questions like every once in a while, and this is one they changed a little bit. Please tell me if you get that one wrong. Everything else here is awesome. Do not ban this question. Do not ban it. I guess it has a little bit of skew. Tiny bit of right skew. You see a little Monster Man's tail? He's got a little tail. Little tiny tail. Little tiny tail. Normal. And that is the large enough n condition right here. Large enough n condition right there. So we will be doing more questions coming up here later. These are really good. Tiny, little tiny. So the more skewed it is, the larger n needs to be. So how large of an n would we need for that? About how large of an n would you need for that? About how large of an n would you need for that one? The more skewed it is, the larger n needs to be. So if it's heavily skewed, you would need a sample size of what? 100. The metrics I go by, and we go by on the test, are if it's skewed, 25. If it's heavily skewed, 100. But if it's normal, the sample size could be like 2, technically speaking. And I can show that. I will show them. I will prove this at the end of this. If you're still watching this video, I'm going to prove this mathematically. Rick Sanchez was once said, I'm going to prove this. You see that distribution? How does that distribution look? How does that distribution look right there? You'll see this in class day. How does that distribution look? It looks very what? I can prove it mathematically. It looks normal. So if I take samples of size 2 from it, you see there's 2 samples, and I take the mean of it. So this is the distribution of means of sample size 2. And I keep doing this process right here where I take samples of size 2 and take the mean of it. This new distribution down here will actually look, oh my gosh, normal. But let's say the distribution up here is heavily skewed. Do you see how this is heavily skewed? Now the distribution up top is heavily skewed, and if I take the distribution of sample size 2 from it, it will still be skewed. So we did not take a large enough sample for the distribution of the mean. You're welcome, Victoria. Move buildings, but I got to move buildings. So now it's not normal. Now, technically, sometimes with this applet, I can't get it skewed enough. Let's see if 25. Look, you see a little skew? So what sample size would you suggest for this? What sample size would you suggest for this? What sample size would you suggest for this? You'd say it's heavily skewed. Mossman is which one is that, engineering? I would say we should take a sample size of at least what? It's heavily skewed. I'm going to call it heavily skewed up there. Because if your sample size is too small, the distribution of the sample mean will not be nearly normal. So notice as I increase sample size, it starts to become more normal. So probably, since it's massively skewed, you should probably take a sample size closer to what? Since it's massively skewed, you should probably take a sample size closer to what? 100. Great job right there, Evan. That's the nearly normal condition, the large enough N. I got to send out the reminders for class. We'll be doing more of these review questions later on. These are tough, but it really comes down to practice. Until then, bye for now, everyone. Bye.